Welcome to Future Human Science. Today, we're delving into one of the most mind-bending concepts in physics, quantum entanglement. Often described as spooky action at a distance, entanglement challenges our understanding of reality and how particles interact. Let's explore what quantum entanglement is, how it works, and why it's considered one of the most fascinating phenomena in quantum physics. Quantum entanglement is a phenomenon where two or more particles become interconnected in such a way that the state of one particle directly affects the state of the other, no matter how far apart they are. This strange and counterintuitive behavior is a fundamental aspect of quantum mechanics, the branch of physics that deals with the behavior of particles on the smallest scales. To understand entanglement, let's start with a basic principle of quantum mechanics: superposition. In quantum physics, particles such as electrons and photons do not have a single, well-defined state. Instead, they exist in a superposition of multiple states simultaneously. For instance, an electron can be in multiple energy levels or locations until it is measured, at which point it collapses into a single state. Now, let's introduce entanglement. When two particles become entangled, their quantum states are linked in such a way that the measurement of one particle's state instantly determines the state of the other, regardless of the distance separating them. This means that if you measure the spin of one entangled electron and find it to be up, the spin of the other electron will immediately be down, even if it's light years away. This instantaneous connection defies our classical understanding of information transfer and suggests that particles can influence each other faster than the speed of light. The concept of entanglement was famously criticized by physicist Albert Einstein, who referred to it as spooky action at a distance. Einstein, along with his colleagues Podolsky and Rosen, proposed the EPR paradox in 1935, arguing that quantum mechanics was incomplete and that entanglement implied that information was being transmitted faster than light, which seemed impossible according to the theory of relativity. However, experiments over the decades have supported the reality of entanglement. In the 1960s, physicist John Bell formulated Bell's theorem, which provided a way to test the predictions of quantum mechanics against those of classical theories. Experiments conducted in the 1980s and 1990s, notably by Alain Aspect and his team, confirmed that entangled particles do indeed exhibit correlations that cannot be explained by classical physics, validating the phenomenon of entanglement. Entanglement has significant implications for various fields of science and technology. In quantum computing, entanglement is used to create qubits, the fundamental units of quantum information. Unlike classical bits, which are either 0 or 1, qubits can represent and process multiple states simultaneously due to superposition and entanglement. This capability enables quantum computers to perform complex calculations much faster than classical computers for certain problems. In quantum cryptography, entanglement plays a crucial role in secure communication. Quantum key distribution, QKD, uses entangled particles to exchange encryption keys with a level of security that is theoretically unbreakable. If an eavesdropper tries to intercept the key, the entanglement between particles will be disturbed, revealing the presence of the intruder. Entanglement also has potential applications in quantum teleportation, a process where the state of a particle is transferred from one location to another without physically moving the particle itself. This is achieved by entangling particles and then using their shared state to reconstruct the particle's quantum information at a distant location. Despite its groundbreaking implications, entanglement remains a deeply perplexing phenomenon. It challenges our classical notions of locality and causality and suggest that the universe operates according to rules that are fundamentally different from our everyday experiences. The continued exploration of quantum entanglement promises to deepen our understanding of the quantum world and its applications in emerging technologies. If you enjoyed this dive into quantum entanglement and want to stay updated on the latest advancements in science and technology, be sure to subscribe to our channel and hit the bell icon for notifications. We'd love to hear your thoughts on quantum entanglement. What aspect of this phenomenon fascinates you the most? Share your comments below. Thank you for joining us on this exploration of quantum entanglement. Until next time, stay curious and keep exploring the wonders of science and technology.